All right, so imagine you're in your chemistry lesson, and you've got this test tube in front of you.
Okay.
And inside is this mysterious substance.
Right?
It could be anything, right? A white powder or maybe some sort of liquid, totally clear.
It sounds intriguing. You've got to figure out what it is.
Exactly. Like some kind of detective, but for chemicals, you
I
know.
love that. A chemical detective.
That's exactly what chemical analysis is all about, isn't it?
It really is. And it's a huge part of chemistry, being able to identify different substances. And in this deep dive, we're going to really get into how to do that. We'll cover everything from figuring out if something's pure
Okay.
to figuring out what's in a mixture, even looking at gases and ions and things like that.
So basically all the clever techniques and stuff.
Yeah, all the tricks of the trade.
Some simple, some maybe a bit more high-tech.
You got it. Some you can do just by looking. Others you might need some special equipment for.
Right. And each one gives you like a clue to what this mystery substance is.
Yeah, like pieces of a puzzle.
Exactly. And what we're aiming for today is to give everyone listening a proper grasp of how chemical analysis works
Absolutely.
and the different methods you can use, which is, well, it's all GCSE stuff, isn't it?
Yeah, spot on.
So let's start with purity. What does it actually mean for a substance to be pure from a scientific point of view?
So when we say pure in science, we have a very specific meaning.
Okay.
It means the substance is made up of just one element or just one compound,
Okay.
and nothing else is mixed in.
Gotcha.
So like if you've got pure water, it's
Yeah.
just HO molecules, nothing else.
Right. Pure magnesium would be just magnesium atoms.
Exactly, just magnesium atoms, and that's it. Nothing else is in there at all.
That makes sense in the lab, but like in everyday life, I feel like we use pure a bit differently.
Oh, for sure.
Like you see pure apple juice on a carton at the supermarket.
Yeah, yeah. And what they usually mean is that it's like natural.
Right. Like nothing artificial added.
Exactly. So like pure milk still has water and fats and proteins and all sorts in it, but it just means they haven't added anything extra.
Okay. So it's a bit more loosey-goosey.
Yeah, definitely.
But in the lab, we can actually test for purity properly, can't we?
Oh, yeah, absolutely. And that's where melting and boiling points come in.
Yeah, I remember learning about that.
So a pure substance will melt at a very precise temperature.
Yeah.
And the same goes for its boiling point.
Like pure water boils at 100 degrees Celsius, right?
Exactly. 100 degrees Celsius at standard atmospheric pressure.
Right.
But if you've got impurities in there, it messes things up.
How so?
Well, imagine the particles in a solid are all connected by these tiny springs.
Okay, I can picture that.
And when you heat it up, those springs vibrate more and more.
Yeah.
And the melting point is when those vibrations get so strong that the springs just snap and the solid melts into a liquid.
Right.
Now, impurities are like throwing sand in the gears. They mess up that nice arrangement of particles, make it easier to break apart, or sometimes harder for the particles to escape.
And that changes the melting and boiling points.
Exactly. It might melt at a lower temperature or boil at a higher one.
And it won't be that precise temperature anymore.
Right. It might happen over a range of temperatures instead of just one specific point.
Interesting. So by measuring those temperatures carefully,
Yeah,
we can get a pretty good idea of how pure something is.
exactly.
Okay, that's pure substances. But what about formulations?
Oh, formulations are really interesting.
Because they're mixtures too, right?
They are, but they're special because they're mixtures designed for a specific purpose.
So not just any old mixture.
No, it's not random at all.
Okay.
Formulations are carefully put together. Each ingredient has a specific job to do.
Like a recipe, but for chemicals.
Exactly. And they're mixed in precise amounts to make sure the final product works exactly the way it's supposed to.
Okay, so what kind of things are formulations then?
Loads of everyday stuff, like the
Yeah.
fuel you put in your car.
Right, I wouldn't have thought of that.
It's not just one chemical, it's a blend.
Makes sense.
And cleaning products, they're full of different chemicals that work together to get rid of dirt, kill bacteria.
That sometimes make things smell nice.
Exactly. And paint is another great example. It's got pigments for the color, binders to make it stick, solvents to make it spread evenly.
And what about medicines?
Oh, medicines are carefully formulated too, of course. You've got the active drug ingredient.
Yeah.
But then loads of other things to make sure it's safe and effective.
Right. And are alloys formulations too?
Yep. Alloys are mixtures of metals that are designed to have specific properties.
Like being stronger or not rusting easily?
Exactly. And then you've got fertilizers, which are formulated to give plants the nutrients they need.
Wow, so many things. Even the food we eat, a lot of that's formulated, isn't it?
It is. Getting the recipe just right is super important.
So we've talked about pure substances in these designed mixtures, formulations.
Yeah.
But what if you've got a mixture and you want to actually separate it out, see what's in it?
That's where chromatography comes in.
Chromatography. That sounds pretty high-tech.
It's a really clever technique, and it's all about separating those different substances in a mixture and
Yeah.
helping us figure out what they are.
So how does it actually work?
So the basic idea is you've got two phases, a stationary phase which doesn't move,
Right.
and a mobile phase which does.
Okay.
And the separation happens because different substances are attracted to or dissolve in those phases differently.
Right.
So some substances will stick more to the stationary phase and not move very far,
Yeah.
while others prefer the mobile phase and travel further with it.
So it's almost like some ingredients are stickier than others.
Exactly.
Yeah.
Like they're clinging on for dear life, while others are happy to go with the flow.
I like that analogy.
Now, when you do
Right.
chromatography, you might come across something called the RF value.
RF value. Okay.
It's a way of measuring how far a substance has traveled compared to the solvent. You calculate it by dividing the distance moved by the substance by the distance moved by the solvent.
So it's like a ratio.
Yeah,
Yeah.
exactly. And because different compounds dissolve and interact with the phases differently, they have different RF values.
Makes sense.
And those values can change depending on the solvent you use.
So if you're trying to identify an unknown substance,
Yeah,
you could compare its RF value to known substances.
exactly. You do the chromatography under the same conditions.
Right.
And if the RF values match, it's a good clue.
So if I did chromatography on a pure substance, what would I see?
You'd only see one spot on the chromatogram no matter what solvent you use.
Just one spot. Interesting.
But if you had a mixture,
Yeah,
you'd likely see multiple spots.
because each substance would travel a different distance.
Exactly. One common type of chromatography you'll probably use is paper chromatography.
Yeah, paper chromatography. We've done that at school using inks and stuff, separating out the colors.
Spot on. It's a really simple but effective way to see the different components in a mixture.
So with paper chromatography, the paper is the stationary phase,
Yeah,
and the solvent, like water or ethanol, is the mobile phase.
exactly. And the different components of the ink, for example, travel different distances up the paper depending on how soluble they are in the solvent.
So we've looked at how to check for purity and how to separate mixtures.
Yeah.
Now, what about identifying specific substances? Like, say you had a gas. Are there tests for that?
Oh, yeah, for sure. There are some classic tests for identifying common gases.
Like the one for hydrogen with the burning splint.
Yes. The squeaky pop test.
Right. So how does that work again?
So you collect the gas in a test tube,
Okay.
and then you carefully bring a lit splint to the opening.
Yeah.
And if it's hydrogen, it'll react with the oxygen in the air and make that squeaky pop sound.
So that's a pretty sure sign it's hydrogen.
Yeah, it's a pretty reliable indicator.
Okay. And what about oxygen, the gas we breathe?
You can test for oxygen using a glowing splint.
A glowing splint.
So
right.
you light a splint, blow it out so it's just glowing, and then you stick it in the test tube with the gas.
Okay.
And if the splint relights, that means it's oxygen.
Because oxygen supports burning.
Exactly. It provides the oxygen needed for combustion.
Okay. So burning splint for hydrogen makes a pop. Glowing splint relights in oxygen. What about carbon dioxide?
Carbon dioxide, now that one involves lime water.
I thought so.
So you bubble the gas through lime water, which is a solution of calcium hydroxide.
Right.
And if there's carbon dioxide present, it reacts with the calcium hydroxide
Uh-huh.
and forms calcium carbonate,
Okay.
which is insoluble, so it makes the lime water turn cloudy.
So cloudy lime water equals carbon dioxide.
You got it. And finally, we've got chlorine.
Chlorine, that one has a very strong smell, doesn't it?
It does, quite pungent, you might say.
Okay.
For chlorine, you use damp litmus paper,
Right.
and you put that into a container with the gas.
And what happens?
The chlorine bleaches the litmus paper.
So it loses its color.
Exactly, it turns white.
Okay, so those are the tests for the common gases. Yep.
Those are some good ones to remember.
But what about ions in solution? Is it trickier to identify those?
It can be a bit more involved, but there are some clever chemical tests for ions too.
Okay.
And then there are more advanced methods that use instruments.
Right. Let's start with the chemical tests. What are some of those?
Well, you might have seen flame tests done in the lab.
Oh, yeah, flame tests. You dip a wire loop in a solution and then stick it in a flame, and the flame changes color.
Exactly. Different metal ions give the flame a different color.
So how does that work?
When you heat up metal ions, the heat gives their electrons energy, making them jump to higher energy levels.
Okay.
But then they fall back down.
Right.
And when they do, they release that energy as light.
And that's what causes the color.
Exactly. And the color depends on the specific metal ion.
So, for example,
Well, lithium compounds give a crimson flame, sodium's a bright yellow, potassium is lilac, calcium's orange-red, and copper is green.
so you can tell which metal ion it is just by the color of the flame.
You can get an idea, but it's not foolproof, especially if you have a mixture of ions.
Right, because the colors might mix together.
Yeah, and some colors can be much stronger than others, like sodium's yellow can easily mask other colors.
So it's a good starting point, but not always the definitive answer.
Precisely.
What other chemical tests are there for ions? I remember something about adding sodium hydroxide and looking at the color of the precipitate.
Oh, yeah, that's a really useful one.
So how does that work?
When you add sodium hydroxide solution to certain metal ions, it can form an insoluble metal hydroxide.
And that's the precipitate.
Exactly. It's a solid that forms in the solution, and the color of that precipitate can tell you a lot about the metal ion.
So like what colors would you get?
Well, if you add sodium hydroxide to aluminium, calcium, or magnesium ions, you get a white precipitate.
Right.
But there's a little trick with aluminium. If you add excess sodium hydroxide,
Yeah.
the precipitate dissolves again. So that's how you can distinguish aluminium from calcium and magnesium. Their precipitates won't dissolve.
So white precipitate that dissolves in excess sodium hydroxide means it's aluminium.
Exactly. And then you've got copper 2, which forms a blue precipitate.
Yeah.
Iron 2 gives a green precipitate, and iron 3 a brown one.
So different colors for different metal ions, that's handy. And what about the equations for these reactions?
Right. So the general equation is that the metal ion reacts with hydroxide ions to form the metal hydroxide.
Okay.
And you need to make sure the charges balance on both sides.
Like how?
So, for example, if you have a metal ion with a 2+ charge,
Yeah.
it will react with 2 hydroxide ions, which each have a 1 charge,
Right.
to form a neutral metal hydroxide.
And all the other ions in the solution, they just stay dissolved.
Yeah, they usually form a soluble compound that doesn't precipitate out.
Okay, that makes sense. So what about carbonate ions? How do you test for those?
Carbonates are fairly straightforward.
How so?
They react with dilute acids to produce carbon dioxide.
Oh, and then you can test for the carbon dioxide.
Exactly. You bubble the gas through lime water, and if it turns cloudy, you know you had carbonate ions.
Right, because that means carbon dioxide was produced.
Precisely.
Okay, what about halide ions? I think that one involves silver nitrate.
You're absolutely right. To test for halides, which are chloride, bromide, and iodide ions,
Yeah.
you first add a little bit of dilute nitric acid.
Okay, why is that?
That's to remove any carbonate ions that might interfere with the test.
Makes sense.
Then you add silver nitrate solution,
Right.
and the different halide ions react with the silver ions to form precipitates.
Right.
But the precipitates have different colors.
So you can tell which halide it is by the color of the precipitate.
Exactly. Silver chloride is white, silver bromide is cream, and silver iodide is yellow.
White, cream, yellow.
Mhm.
Is there an easy way to remember that order?
There's a mnemonic some people use. Cats with brains can ideally yodel.
Cats with brains can ideally yodel.
Chloride, bromide, iodide, white, cream, yellow.
Clever. That'll definitely help me remember.
Excellent. And lastly, we have sulfate ions.
Okay, how do you test for those?
For sulfates, you add a few drops of dilute hydrochloric acid
Okay.
and then some barium chloride solution.
And what are you looking for?
If a white precipitate forms, that's barium sulfate, and it means sulfate ions were present.
So those are all the chemical tests for different ions.
Yep, quite a few to remember.
But the notes also mention instrumental methods. What are those all about?
Instrumental methods are techniques that use, well, instruments to analyze substances,
Okay.
and they have some big advantages over the chemical tests we've been talking about.
Like what?
They're generally much more accurate and much more sensitive.
Sensitive.
Yeah, means they can detect really tiny amounts of a substance,
Oh, wow.
and they're often much faster too.
So they're really useful in situations where you need quick and precise results.
Exactly. They're used in all sorts of industries and research.
And one example mentioned was flame emission spectroscopy.
Right, that's a really cool technique.
So how does that one work?
So it's specifically for analyzing metal ions in solution.
Okay.
You take a sample of the solution and put it into a flame.
Like in the flame tests.
Similar idea, the heat excites the electrons in the metal ions.
Yeah.
And when the electrons fall back down, they emit light.
Right.
But in flame emission spectroscopy, that light is passed through a spectroscope.
A spectroscope. What's that?
It's an instrument that splits the light into its different wavelengths.
Oh, like a prism.
Exactly. And it creates a unique pattern of lines called an emission spectrum.
So each metal ion has its own unique pattern.
Yes, like a fingerprint.
Wow. So by analyzing those lines,
Yeah,
you can identify which metal ions are present.
exactly. And you can even tell how much each ion is there.
That's amazing. So
Yeah.
much more detail than just seeing a colored flame.
It's incredibly powerful.
So we've covered so much, from simple melting and boiling points
Yeah.
to chromatography, all those chemical tests,
Yep.
and now this really sophisticated flame emission spectroscopy.
That's quite the toolkit for chemical analysis.
It is all these different techniques.
They all play a part in helping us understand the world around us.
And it's not just in the lab, is it?
No, not at all.
All this knowledge is used in so many real-world situations.
Absolutely. Think about food safety, making sure our food is free from harmful contaminants.
Right.
Or testing our water quality.
It's important stuff.
It really is. And the techniques we talked about, they all have their place.
It's pretty amazing how many different ways there are to figure out what things are made of.
It is, isn't it? It's like being a detective, but for the building blocks of the universe.
I like that. And out of all these methods, which one do you find most fascinating?
That's a tough one. They all have their own unique appeal, but I think for me, it has to be flame emission spectroscopy.
Really? Why is that?
It's just so elegant, the way you can identify and quantify metal ions just by analyzing the light they emit.
I can see why you'd find that fascinating.
Ugh. And it has so many applications, from environmental monitoring to analyzing the composition of stars.
It's incredible to think we can analyze things that are so far away.
It really is. It just shows how powerful these techniques can be.
Well, I think we've covered a lot today.
I think so too.
And hopefully everyone listening has a much better understanding of how chemical analysis works.
And maybe even inspired a few future chemical detectives.
That would be amazing.
It would. It's such a fascinating field, full of challenges and discoveries.
Well, on that note, I think it's time to wrap up.
Sounds good to me.
Thanks for joining us for this deep dive into chemical analysis.
It's been a pleasure.
And to all you listeners out there,
Yes,
keep exploring the world of chemistry. You never know what amazing things you might discover.
absolutely.
Until next time.
See you then.